Okay, so next video is part 116. This is line 18, a3m Fermions Bosons Lepton spin Electrons Pauli Exclusion Principle Wow Seti. There's the signal there. We're going back to the source from the last video. I found a statement that I missed. February 4th, 2012. My thoughts on source distribution from video number 115, line 18A3K. This comes to mind as soon as I read this portion of data. It can be used for the mirrors on the space elevator idea. I think you would use these mathematical calculations. February 4th, 2012. My thoughts. I finally figured out what a fermion is, and this comes up in the alien message from January 21st, 2012. Fermions and E, maybe the E isn't for Euhlers Numbers or equations, maybe it's for electron. The electron symbol E is a subatomic particle with a negative elementary electric charge. It has no known components or substructure. In other words, it is generally thought to be an elementary particle. An electron has a mass that is approximately 1836 that of the proton. The intrinsic angular momentum spin of the electron is a half integral value in units of whatever that is, which means that it is a fermion. The antiparticle of the electron is called the positron. It is identical to the electron except that it carries electrical and other charges of the opposite sign. When an electron collides with a positron, both particles may either scatter off each other or be totally annihilated, producing a pair or more of gamma-ray photons. Electrons, which belong to the first generation of the lepton particle family, participate in gravitational, electromagnetic, and weak interactions. Electrons, like all matter, have quantum mechanical properties of both particles and waves, so they can collide with each other's particles and be diffracted like light. Since the electron is a fermion, no two electrons can occupy the same quantum state in accordance with the Pauli exclusion principle. In many physical phenomena, such as electricity, magnetism, and thermal conductivity, electrons play an essential role. An electron in motion relative to an observer generates a magnetic field and will be deflected by external magnetic fields. When an electron is accelerated, it can absorb or radiate energy in the form of photons. Electrons, together with atomic nuclei made of protons and neutrons, make up atoms. The attractive Coulomb force between an electron and a proton causes electrons to be bound into atoms. The exchange or sharing of the electrons between two or more atoms is the main cause of chemical bonding. Laboratory instruments are capable of containing and observing individual electrons as well as electron plasma, whereas dedicated telescopes can detect electron plasma in outer space. Electrons have many applications, including welding, cathode ray tubes, electron microscopes, radiation therapy, lasers, and particle accelerators. The Pauli exclusion principle is the quantum mechanical principle that no two identical fermions, particles with half-integer spin, may occupy the same quantum state simultaneously. A more regular statement is that the total wave function for two identical fermions is antisymmetric with respect to exchange of the particles. The principle was formulated by Austrian physicist Wolfgang Pauli in 1925. For example, no two electrons in a single atom can have the same four quantum numbers. If n1 and m1 are the same, ms must be different such that the electrons have opposite spins, and so on. Integer spin particles, bosons, are not subject to the Pauli exclusion principle. Any number of identical bosons can occupy the same quantum state as with, for instance, photons produced by a laser and Bose-Einstein condensate. Fermions, particles with antisymmetric wave functions, obey the Pauli exclusion principle. In addition to the electron, proton, and neutron, these include neutrinos and quarks, the constitution particles of protons and neutrons in some atoms such as helium-3. In the theory of quantum mechanics, fermions are described by antisymmetric states. Particles with integer spin, called bosons, have symmetric wave function. Unlike fermions, they may share the same quantum states. Bosons include the photon, the copper pairs, which are responsible for superconductivity, and W and Z bosons. Fermions take their name from the Fermi-Dirac statistical distribution that they obey, and bosons from the Bose-Einstein distribution. So that's the end of that video. Next is going to be N.